Hello. Today we want to discuss a special type of bridges. Even a normal bridge is an advanced topic for every engineer. And there's one type called movable bridge, or at least a bridge that can be opened, that's even harder for to design because there are more types and it's even more advanced to design a movable bridge. So in this presentation, we want to discuss the difference of a movable bridge to a normal bridge, and also the static parts of it, what is important to know about movable bridges. I know that even now you don't have your presentation or the subject about bridges in your schedule, but it's not that deep into, so I hope it's also possible for you to understand. First of all, there has to be a good reason to build such a bridge. To make a bridge openable, it's so much more expensive than it's for a normal bridge. So you're just constructing one when it's absolutely needed. Yeah, first of all, a movable bridge is normally built over a waterway, so a ship down under, and the bridge opens when there's a ship coming that is too high to get underneath. And the problem there is that at some points the land level is so close to the sea level that it needs so much space to build a ramp, to construct a bridge that is higher level than it would be at a movable bridge. So, for example, it would be way cheaper to construct a normal bridge that is high enough for a ship to pass, and also for a car or a train, whatever, or a pedestrian, whatever, to passing on top of the deck. That's also a reason or a problem for a movable bridge. When the bridge is opened, then it's not possible to pass in the top way. So, for example, for a car, it's not possible to pass. But when it's closed, it's not possible for every ship to pass this knot and this place. So you're constructing a bridge that is more expensive than a normal one, and it's also not possible to pass at every time, every way it's crossing. Yeah. And the next reason is mostly a reason that is at every constructing everything special, then it has to be an architectural reason. So, for example, we will see a picture later where some special things are just for optics are constructed, and maybe there would be a possibility to build them more easily, more cheap. Yeah, and the last reason, that's not our topic here at all, but I want to mention it. In history, there has always been a type of movable bridge. It's a drawbridge. At every castle, or nearly every castle in Middle Age, there has been a drawbridge, and there it has been for military reasons. So it's just possible to pass when you want to. And even today, there are some vehicles that can construct a bridge temporarily.
In our city, Gdansk, we have an example of a movable bridge. As part of the regeneration of the old center of Gdansk, a series of bridges are being built to reconnect the Granary Island and Olowianka to the main city. Both sides of the river would have been thriving centers of industry and commerce, but despite the island's proximity to the center, they have recovered slowly from the deconstruction of the Second World War. While new development of Granary Island will see a bridge appear close to the crane, another is already in place. Measuring 70.5 meters in length and varying in height from 6.76 to 10.56 meters and costing 10 million zloty, the new bridge connects the riverbank next to the Prolog and Kubiki restaurant near the Hilton with the Polish Baltic Philharmonic building opposite on Olowianka. The bridge is designed to be able to swing upwards to open to allow sweeping to pass through, and this process takes as little as 2 minutes. The official opening took place on 17 of June 2017 and has already markedly improved the flow of people through the island and opened up a part of the city which had felt cut off for many years.
Here you can see what is so special about the movable bridge. Right here at this point the bridge is closed. So at this point you can see on the left hand side there is a fixed support. On the right hand side there's a hinged support. So at the left hand side you can imagine there is a negative moment, bending moment for this bridge, and in the field in the middle there's the positive one. A few seconds later, the support on the right hand side is gone. So now it's just a normal cantilever where every bending moment all over the bridge is negative. At the end of the opening process, the bridge is nearly vertical. So right now it's more like a column than it is like a bending beam. In the whole opening process, there are several parts of the bridge that changed from compressive to tensile to compressive stresses, and even by clothing back then. So it's very important for a movable bridge to have a material that is isotropic, that can load with tensile and compressive strains and stresses as well.
Of course, building a bridge has to consider a lot of factors. Some of them are atmospherically factors, and we can't forget that Gdansk is always exposed to the wind. The action of the wind could be assimilated to the conventional horizontal static load, perpendicular to the axis of the bridge, on the most adverse direction. We can also have snow, rain and storm, for example, and all of them compromise the exercise of the bridges. Another important factor is the danger of the loads. During the project, it must be considered how many loads every day cross the bridge: cars, trucks, people. Considering Gdansk 1 is just open for bicycles and pedestrians. Sometimes there is the necessity to consider also the hydraulic compatibility, that is, the proximity to the flows of the rivers or of the sea. This factor can compromise the exercise of the bridge during the years. In fact, the most of them have been corroded by watercourses. We have considered also impress deformations, distortions and pre-stresses. Both are foreseen during the project. Rheological effects, retirement and viscosity, and it is caused by the retirement of the concrete and the thermal variations, and constraining failure. This is really important in particular to foresee the structural failure. The principal causes of misalignment are derived from errors in machining, misunderstanding of the need for tolerance controlled by designers, and improper installation of racks, bearings, shafts, tracks, tread plates, pinion gears. Structural elements used in construction of movable bridges are another source of misalignment. Rolled sections and plates have some degree of lack of straightness, twist, and camber. The relief of residual stresses during longer-term operation of the bridge can also cause plastic deformation and distortion. The long-term mechanical action and vibration of machine elements and structures can lead to loss of rigidity. Because movable bridges use heavy, they are subject to dropping over long periods, particularly if the tracks or foundations have insufficient capacity to handle concentrated loads typically not scaled by fixed bridge piers. The use of modern laser positioning and laser theodolites have markedly improved our misunderstanding of misalignment in movable bridges.